So in the second part of the lesson, now we are going to look at applications of what we learned in regards to current carrying wire, which create magnetic fields and then may interact in very interesting ways with other magnetic fields. This becomes very useful. Because of these interactions, we are able to create something called a motor, which we've all heard of. A motor is a device that begins with a chemical energy in a battery and turns it into mechanical energy. We can then make a loop wire spin, and this spinning loop of wire can be hooked to many devices that require motion, such as an electric lawnmower, fans, axles, and so on. So here, we have a St. Louis motor for us to examine and how we can apply what we learned so far to the St. Louis motor to figure out how it works. So let's start off here. These metal pieces here on this side and this side, these are called my brushes. Now my brushes are going to be connected to a power source. So let's say this brush here is connected to the negative. So my negative charge is going to come down like this and my positive's there. So we have a circuit here. Now the brushes, they don't connect, but they brush against a commutator. That's why they're called a brush, and we'll get why we want them to brush and not permanently connected to this commutator. So this copper piece here is going to be called a commutator. Now, the brushes send electrons to the commutator, and then they come down here. And if we follow this coil, we see how it ends. It comes up this way, loops around, and we'll see on this side, it loops around and comes down. So my electrons come up, they loop around and come down all the way here, and then they follow around through the bottom of this one here. Okay? So let's look that over. Now, we're looking at this. We have current that is going through wires that are wrapped around an iron piece of metal. Okay? So this here is a solenoid. And we already learned we could use our left-hand rule because we're looking at electrons for a solenoid. So if I look at that, we discovered that the current is coming up because the wires are coiled up and they go around and down. So if they're coming up and they go around and down, we use our fingers for a solenoid, if we remember, to figure out the current motion. So they're coming up in front and they're going around and wrapping down. My thumb represents my magnetic lines. So the direction of my magnetic lines are going to go out that way and in this way. So if we bring back our motor here, and I'm going to turn it. So basically I'm looking at this. If it's happening like that, it's coming up that way, this is going to have to be my magnetic north, because my north comes out, the magnetic lines come out of the north and into the south. And if we remember, this follows right through, it's wrapped around, so this comes down and up that way. So it's still, because it comes down in the back here, it's going to come down in the back and up around. So this still reinforces that this side's magnetic north and that side's going to be magnetic south. Now, let's pretend that this magnet here is south as well. So what's going to happen is these are going to repel each other. So then we put this down here. This is going to repel each other and cause it to spin this way until it comes all the way across like this. Now when it hits here, we have north and south, or we have south and north, and we have north and south. Because remember, we started like this. We said this was the south. The south is going all the way around, and the north is coming all the way around this way. So the north ends up on this side, south's on that side. But now, what would happen is these magnetic fields, they'd be attracted and they want to stay. So that's where this commutator becomes very crucial. So if we go back here, let's look at this. So right now, it's sending the current down this side and up on this side, right? Because we said electrons are on this side, so they're connected to this positive, to this side of the commutator, and this side of the commutator, the other side, the electrons are coming up. So when it keeps on going, if we can see right here when it's going to touch, it keeps on turning, until all of a sudden, it's right here, it breaks. Okay, I'm going to show you right here. It now breaks. So right now there's no current going through. And then the brush turns from this side of the commutator to this side of the commutator. Now it's touching the other side of the commutator. So that is going to end up switching the flow of electrons. So now this side becomes the negative. So what ends up happening here is everything's going down on this side. It's coming down and through this side, okay? So now my current flow reversed. And if my current flow reversed, so let's say before we had it going this way, where this is north, this is south, my current flow reversed in that thing, making it go this way, where now this becomes north and south. So my pattern keeps on rotating. So if I look at it, we're north and south, let's say right there, it's turning, 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 and as my hand turns, uh-oh, this is still north, and let's say this is south, it stays. But according to my commutator, it's separated, and the momentum will keep it moving a little bit until my brush touches the other end of the commutator, and my hand was like this, remember? Following this, my hand was like this. So now the direction of the electrons is going to change. And this becomes my north, and that becomes my south. So this becomes my north, and that becomes my south. And it's going to turn and turn again. And this cycle is going to keep on working. So now I'm going to turn on my power, and we're going to see how this works. So once again, we have my negative coming in here. Well, but my armature kind of spun out. My negative's coming in here, and my positive's coming up there. And if I just let it go, we get that for a little bit of a motor. And that's how my motor works. I could slow it down or speed it up, but right now my brush is kind of moving away. But that's how the cycle of the motor works. So now I have some questions for you that I want you to answer at home. What do you think would happen if I move these magnets here farther apart? Would it affect the speed of which my armature rotates? What would happen if I increase the current flow? Would that affect the rate of which my armature rotates? If I put them closer together, would that affect it? Okay. I want you to think about all of these things and how it affects how my motor works. So let's review the basics of a motor. This part here is called the commutator. This one's a little bit different than the St. Louis motor I showed you. Now if we look at this here, my current flows this way around it, creating a force, right? And we know my formula for my force created by current flowing through a wire is my current multiplied by the length of the wire. So remember, if we had more coils, that would mean, and I wrap this around more coils, that means we have more length going through the magnetic field, which increases my force. We have current increases the force, and then we also have magnetic field increases the force. Now, here we have my stator, which are my magnetic fields. So commutator is right part here. It's normally separated by something. We have my brushes right over here. And then right here we have my armature that turns. So this last section here brings us to a very, very intriguing and cool interaction that we could use to our advantage, and we can make things move by just using electricity and magnetic fields. So let's look at this here. We have a bar magnet. We have current that could possibly go through a carbon rod, and it's going to go this way. Now, this is a keynote thing. The current is going this way. This is red is positive, so red is my positive. We have a positive current flowing through. Now, the carbon rod, to note, is not magnetic, so it's not affected by the magnetic field at first. When no current flows through, the rod is stationary. When we turn on the current, we're going to have to use my right hand because we're looking at positive, so we're using my right hand. Magnetic field's coming down, my current's coming in towards me. That means it's going to push the rod out that way. So the direction of the force is determined by the direction of my current flow.